as you know, we have overlaps between each element. For example, if this is element 1 and this is element 2, this point is common, right? This point is common. And if you have, for example, two equations for element 1 and two equations for element 2, actually, we don't have 4 independent equations. We have 3 independent equations because we have overlap here, because a common point here. So the next step is construction of the global matrix. After constructing a stiffness matrix for each mesh element, we should construct the global matrix. So here you can see this is for element 1, element 2, element 3, and element NE, these equations. And because we have V2 of element 1 is equal V1 of element 2, that is equal V2 voltage of the second mesh node. Because of these equalities, we have overlaps, and we have this important step, that is assembly of global matrix. So for all mesh elements, finally we have this system of equations. This global stiffness matrix and solution vector. Our solution vector is V1 to Vn, right? The solution vector is voltage of all mesh nodes. Actually, we are looking for V1 in this graph to V4. We are going to find these values. Also, we have force vector here and a vector here that is displacement current. But we can consider an approximation here. When the number of mesh elements are sufficiently large number, we can consider this assumption here. Minus d2 of element 1, for example, plus d1 of element 2 is approximately equal to 0. Equal to 0. So here, this is the value of d vector, that all elements inside it is equal to the 0. So now we are going to implement this example for our problem, and then we learn how we can apply boundary conditions, and finally solve the global system of equations. So we should calculate the stiffness matrix and the load vector, and then assemble them, and finally apply boundary condition and solve. So you can see this pseudocode for assembling the global stiffness matrix and force vector that I will explain it now. So, do you have any question about assembly of elements?
No, it's clear.
Okay. So, now let's write this code. Here, I write a comment, allocate memory for a stiffness and a stiffness matrix and load vector. This is a stiffness matrix. I want to allocate memory. The stiffness matrix, what is the dimension of a stiffness matrix? Is n by n. Actually, we are going to solve the equation. We are going to find the value of solution variable for each mesh node. So the number of mesh nodes is equal nn, and the stiffness matrix is nn times nn. The load vector is nn times 1. So this is the load vector, and this is a stiffness matrix. So I allocate memory here. I write zeros nn and nn. Also, I write here f, force vector, zeros of nn and 1. However, this is not a good way. This is not a good way because, as you can see here, most of elements of the stiffness matrix are equal 0. So we should use a sparse matrix calculations to be able to solve large problems. I will explain when we study finite element method for two-dimensional and when we want to consider large meshes, right? But here, for the sake of simplicity, I consider these two functions for allocation, but later we will use a sparse matrix calculations. So here I write global assembly. So I should have 2 for loops, as you can see here. The first for loop is our mesh elements, and the next for loop is our each mesh nodes. Also, you can split this for loop into 2 for loops if you want, or 1 for loop only. I will explain this. So I write here I write for I equal 1 to ne number of mesh elements, for j equal to 1 to 2, and I have 2 nodes per each mesh element. So I write k. Actually, if you consider this part here, this is k11 of 1, k21 of 1, and k12 of 1, and this summation here. So in this example, because we considered equally spaced points, the value of LE for each mesh element is equal. But you can consider a non-uniform mesh distribution. For example, instead of equally spaced points, you can consider this. So the mesh element length here is lower than the mesh element length here. So for generalization, I calculate the mesh element length. So here I write the comment, calculate mesh length. I write for I equal to 1 to NE and this is mesh length of mesh element. I allocate the memory, zeros, 1 and number of elements. So what is the LEI is equal x of what? Connectivity list I and 2. We should calculate this after calculation of the connectivity list here. Minus this. So this is why we defined connectivity list. Let me explain this part of the code. This is the element number I. So what is this? Is the second node, index of second node of element number I. I want to pick up its x value, and this is the first node. So I know LE is equal x2e minus x1e. So if I place a breakpoint here and run, as you can see here, the value of LE is the same for all 4 elements. Now, here, let's construct, for example, this part for the first element. As you can see, we have these values. Values for each mesh element. This is 1, minus 1, minus 1, and 1. So, according to this value, I can write K connectivity list of I and 1 and let me also remove this for loop. Later I will consider this for loop. This is just for simplicity in the code. I don't want to write a complex code now. So this is 2 for loops. We have 2 for loops here, but I don't want to explain in this way. I want to write a simple code and later we will modify it. As you can see here, we have 2 equations and we should add 4 elements, or we should modify 4 elements of the stiffness matrix. This is Ki11 of element 1. So here, this is element number I and 1 element. So I should write this is equal this plus epsilon E divided by LE times 1. This is 1, right? So here I write the value of epsilon. The value of epsilon is equal E0 times ER. Here I can write E is equal E0 times ER. the permittivity of the element. So we have this here, E divided by LEI times 1. This is 1, not important. So I copy this, paste, paste, paste. I am going to modify 4 elements. This is K12 of element 1, right? K12 of element 1. K12 of element 1 is this expression times -1, right? Times -1. So this is negative. And K21 is negative. K22 is summation because sometimes we have overlap. So you should sum up the previous value plus the new value. So we have this assembly here for this modification for each mesh element. And we have force vector. I write here, this is a stiffness matrix, and this is the force vector. How we modify the force vector? Using this equation, or what was the value of force vector is negative of LE times rho naught divided by 2, 1, 1. So I write here, this is equal this minus LEI, this element, times rho 0. We have the value of rho 0 here, divided by 2. Divided by 2. Also, I have the same summation for the second node. For the second node, the value is the same. So if I run this code, we don't have the value of E. Let's run this code again. So we have the value of E now, and run this. So CLC, this is the value of a stiffness matrix. As you can see, this is a symmetric and force vector, right? This is the force vector. So we have a numerical example also here. You can see the values of the stiffness matrix and force vector here. So let's check. Actually, we have a better form here. Let me divide force vector by 1e minus 10 to be able to see it in this form, be able to check its value, because in this numerical example, number of nodes is equal to the 5, and we have this force vector here. But check. Let's check. Okay. Let's check the solution because sometimes we should show numbers in other formats. Anyway, so we constructed the global matrix, global stiffness matrix, and global force vector. So the next step is imposing the boundary conditions. Here, in this example, we have two boundary conditions. We know the value of voltage V1 and Vn, right? According to boundary conditions, V1 is equal V0 and Vn is equal 0 based on boundary conditions, right? So, how we can impose boundary conditions? How we can impose Dirichlet boundary conditions? We have this stiffness matrix and solution vector and force vector. So we have n independent equations that we are going to apply these two constraints. V1 is equal V0 and Vn is equal 0, right? So actually we know the value of two of these unknowns. So I can change their corresponding row. So here I can modify my system of equations in this form. In this form, I can write a comment here imposing boundary conditions left point. The left point is the first mesh node, right? The first mesh node. I can write k 1 and 1 is equal 1. K 1 and let me write this for j equal to 2 to n n n k1 and j equal to 0. Consider this equation. Consider this equation. I want to modify this. I want to modify this first equation. Because I know the value of V1 that is equal to V0, right? So how I can impose? I can set the value of this element equal to 0 and this element equal to 1, right? So using this method, we can impose the Dirichlet boundary condition, right? Is it clear?
Yeah, it's clear.
So using this code, k1 and 1 is equal 1, 2 to nn is equal 0, and f1 is equal v0. For the right point, I can write knn and nn is equal 1, 1 to nn minus 1 equal to 0. This is nn and this is nn is equal 0. Applying the right boundary condition. So this is 0, 0, 0, 0, this is 1, and this is 0. So actually we impose that the value of Vn should be equal to 0. So what is the next step? The next step is solving system of equations. This is the most important or the most powerful syntax of the MATLAB software. Solving system of equations. This syntax. The solution variable V is equal a stiffness matrix backslash F. Actually, we are going to solve this equation. V is equal K inverse times F, right? So I used this MATLAB syntax, K backslash F. K backslash F. This MATLAB syntax. I will explain it later, but you can search in the web and read more about this syntax in MATLAB software. So if I run this code and right here V, you can see the value of V that we calculated using the finite element method, right? So you can see the example, numeric example here that is solved for 5 mesh nodes. For 5 mesh nodes. So if I plot the solution here also, plot xn, and we set its color equal to red. First plot this and then this. So we have a mistake in our code because this is not the correct solution. The correct solution, the value of V3 and V4 is like this. This is V2, V3, and V4. So let's check. Let's check. This is a stiffness matrix, force vector, and element length. This is the assembly method for we have a loop for each mesh element, a loop for each mesh element considering this matrix equation, this standard matrix here, and this is the value of epsilon E, right? Epsilon E. Also we have this force vector. Oh, this is xn, not x. This is mesh element, right? This x is from 0 to the 100. This is for analytic solution, right?
Yes.
And we generated this mesh. So a big mistake. This is the mesh. So let's run this code and this code, and you can see this is the finite element solution, right? Finite element solution. So we implemented the finite element method for this one-dimensional problem, and we replicated the same result that is presented here for FEM, right? So now here you can see the effect of the mesh resolution. If I increase number of mesh nodes, for example, to 10, as you can see here, I have a better solution here now, right, than before. So if I, for example, consider 15, almost the same of analytic solution, right? So yes, here, as you can see, as we increase number of mesh nodes, we can get a better and better solution.